with the support of intermediate pipeline registers. So in that way, we have seen that if we without pipeline, we can calculate that these 5 instructions separately would require 5 into 5. The 5. The different instructions. Sorry, 5. Yeah, 5 into 5 are 25 clock cycles. Whereas this is only requiring 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 clock cycles. But this is the extreme case, or we can say best scenario we can think of. It is not that for each and every instruction set, whatever program you are running, for each and every instructions, you cannot fit in your pipelining sequence so easily. Because you can think, like we can take these type of examples, where you can think these are the 2 consecutive instructions. So in this first one is load word, where you are loading this S0. Okay. But in this add instruction, you can see here you are performing this addition operation based on the inputs from this A0 and S4. Now, if you feed these 2 instructions in your this previous pipeline, you can understand that this A0 with your this load word instruction is getting updated in this phase. Okay. In this clock cycle, this is the 5th clock cycle. Whereas when you are trying to do this addition operation for your next instruction, if you come back, this is your 2nd instruction. So you are actually trying to execute this instruction according to your pipelining scenario in the 3rd clock cycle. Sorry, 3rd clock cycle, right? So in that case, if you are blindly, applying your pipelining strategy to this type of sequences, what will happen? This is 0. Whatever you are getting in this execution phase is not actually updated by your previous instruction. So that means you will not get your desired results, because you are not giving according to your normal instruction flow. You are not giving your proper inputs. So for this reason, this is one example of data hazard. Why? Because whatever data input I'm expecting in this execution phase, we are not getting the same. Similarly, this part is the control hazard. You can see this is for branch if equal. Now this branch if equal, it will actually perform this. If these T0 and T1 both values are equal, then it will branch to this L1. If not, your immediate next sequence is this add, that is your instruction 1 and instruction 2. If no branching is taking place, and if your branching is actually taking place, you have to jump from 1 to 3. That means your instruction sequence will be 1, that next instruction will be L1. But when you are feeding these instructions to, again, this kind of stage pipeline, of course, immediately in the next stage, you are not having the idea, because that time this execution has not taken place. This T0 to 1, T1, whether they are equal or not, that decision making you can do in after the execution phase. So at the cycle 3. But in the 2nd cycle, you are not getting the idea whether you have to execute this add instruction or the sub instruction. So these are the scenarios are called control hazards. So we have typical 2 solution scenarios we generally use. One is forwarding, another is stalling. Now take this example again. This is another example, but this is also depicting the similar scenario. You can see here, this in the sequence of instructions. Again, you are having load word. then you are performing AND, you are performing OR, and in all this AND and OR subsequent instructions, you are basically using this value, correct? But you know now that your due to this load word, you can see at the right, due to this load word, this load word is getting completed here. So whatever the value you are using in this next AND or ON or inputs in your subsequent situation, subsequent instructions, if you are directly following this pipelining strategy, you can see this blue lines are showing all the dependencies. You are using this value here, you are trying to use this value here, that way. Also, you are trying to use value in this add operation. So in all these three cases, what will happen? If you directly follow this pipelining strategy, there is a chance of data hazard. For that, we are trying to propose two solutions. One is forwarding. Forwarding means what we have told, needed data is forwarded as soon as possible to the instruction which depends on it. That means, see, this loading means you are loading to some register and you are fetching that data from some memory location, from some data memory. That means from this data memory, at the end of these instruction cycle, that data is available in your pipeline register. But it maybe the situation is that is not updated in your exact desired register, but the data is available. So the forwarding concept is as soon as possible, if you have that data, just pass them to the required modules or required next immediate pipelining sequences. So here, if this data is available here, we can pass it here, and so on. I mean, wherever the data is required. But will that solve the problem? Because if you see closely, for this OR execution or for this AND execution, this forwarding strategy will be okay. It is fine. If you just, whenever the data is available from this data memory, just pass that on to their execution input. Pass this on to for these instructions to their execution module. But for this AND, to pass that, you have to go, back in time or some, it is not possible. This execution is taking place starting from of this cycle, and at that time, your data is not available. So in that scenario, this only forwarding will also not be sufficient. So the another solution is you can add stall. You can add bubble to your pipeline, or you can add one. Basically, bubble adding means nothing but adding a no operation. No operation means after this loading, you are basically, this no operation means no valid operation is taking place in this pipeline stage. That means you are just adding one bubble. In that way, this is basically adding a delay, nothing. We are adding a delay, and for this reason, when now you are coming to this AND instruction, at that point, if you are considering that, okay, or in the initial part of the cycle, you can fetch the data from the data memory. You can directly in the same stage, you can directly pass that to this register phase or this ALU phase for the execution. So this way, adding one stall is sometimes effective when actually you cannot do direct data forwarding strategy. You cannot take direct data forwarding strategy. So these are two solutions. I hope it is clear to you. One is forwarding. Forwarding means whenever data is available, directly send that. Do not wait for the data finally getting stored to its desired location. And the second one is adding, if that is not working, you are adding one extra delay. Of course, extra delay means you can understand you are doing that. You are doing that. I mean, you are doing in terms of some performance. You are basically, I mean, your main objective of adding pipeline to your hardware to improve your performance. But when you are, I mean, associating that with some delay, that is basically delaying your overall performance. But still, you have to do that to maintain your requirements, because it is no use that if you are doing something you are improving your performance, but whatever you are doing, that is wrong. So that way, these are the two strategies. Next one, yeah.
Ma'am, this NOP, like how much time delay it is providing? Like, do we get to decide that, or just a clock cycle, one clock cycle difference will be created?
Once again, can you repeat?
Uh, Ma'am, like
Voice.
we are using NOP system, like NOP
Yes.
command. So
Yes.
I'm asking, how much time difference will it? How much delay will it create? Like it will be a one clock cycle, or we can decide how
You
much
think from
delay
this diagram, what do you suggest?
a single
What is
clock
your
cycle.
main purpose? Main purpose is that whenever you are coming to this execution phase, sorry, wait. Whenever you are coming to this execution phase, at that time, your data should be ready. Okay. So based on that, it may happen you have to, I mean, in this example, we have just added one stage of bubble. Okay. But there, it may happen in some scenarios, you have to use multiple bubbles. Okay.
So ma'am, like one bubble is just creating a difference of one cycle, one clock cycle, right?
Yes, of course. Your one bubble means you can say one NOP operation. You are adding one extra operation, nothing else. But that that addition of that operation is actually not affecting anything according to your required specification, your required instructions. Those required instructions are not getting executed. Okay, this is not something out of order execution. There is another example we will take. There we will see that is mostly done in case of the superscalar, where you can replace this no operation with some future instructions. You can pick some future instructions and you can execute that here. But that instruction, you should have the clear idea that instruction is not having any dependency with your previous inputs. That is also possible. But here, adding bubble means that adding one extra operation. But that operation is basically no operation, no value. That means typically adding a delay.
Ma'am, what is the duration of the delay? Can you please tell me?
Pardon? No, wait.
What is the duration of the delay? That bubble when we are adding, what's the duration of that delay? So depending upon the
Okay, what is the duration? Now see, it's depending upon that is the scenario. Here, how much delay you have to give? You have to, how much delay means how many no operations you are actually adding. No operations means one single operations, right? One operation means we can tell they will again go through this pipeline, right? Now here, if it is required that in this case, your data memory is giving instruction, output in this stage here. Okay. Now your output required, the value as an input required in this stage. So one stage delay is enough, right? It may happen in some cases the delay required more. In that case, you will add multiple NOPs, multiple bubbles.
okay.
Okay, so it may happen if it would have been here, or based on whatever your instruction scenario. If required, you may need to have multiple bubbles. It is not that only you are just calculating the duration of the bubble or the duration of the delay. That is fixed. you're adding one extra instruction. Now that instruction will follow your instruction cycle and all this. Those are fixed. Only what you can change how many numbers of those no operations you will add. Clear?
Okay.
Okay. So that way you can calculate how much delay you have to put. Okay. This is an example of data hazard. Next, we are coming to control hazard. Now you see again the controller, whatever we have discussed. This is one extended example. You can see what we are doing. There is one branch if equal. After that, there are some subsequent instructions and or add whatever. And if this branch is equal, then I mean what we say, the branching requirement is satisfied, then we will jump to this branch target. Okay. So the main problem you can understand, this is your branch if equal instruction execution. What you have to do here, you have to compute this. You have to do some equality check. That means you have to come up to here. After that, you will get to know whether the equality is satisfied or not. So before cycle 3, there is no way you can know that whether you are taking a branch or not taking a branch. So in such scenarios, the things are not very predictive. So there are different types of solutions actually, not this one, but one typical solution generally designers take, that they execute next instructions. Next instruction means and or add these 3 instructions, added instructions. It may happen if you are taking a branch, there is no value of these instructions. You have to just flush it. You have to just discard it. So in that case, what they do, they just take these instructions, and if branching is taking place after this cycle 3, they will go to that branch instruction execution and just flush this intermediate result from the memory. Okay, maybe you can tell this is some kind of wastage. We are sometimes purposefully executing some instructions that we know that may or may not be required. But there is always a 50-50 chance. Instead of what is the other solution? What you can do else if you are not executing this? You can add some NOPs here. You can add some NOPs. You can add some bubbles, maybe 1, 2, 3 bubbles here. See again, here you are using bubbles based on your requirement, based on the fact you know that you have to go till 3rd cycle. Other than that, you cannot know that whether you have to take the branch or not. So this is a typical example where we are taking multiple NOPs. We may need to have take multiple NOPs. That means anyway you are adding some delay. So anyway you are actually performing some operation that will not be required. But here, if you do this, if you allow this predictive branching, this is called predictive branching, that you are making some anticipation. Okay, let's consider the branching condition will never get satisfied. So with that prediction, you are proceeding with an or an add. So there is in some cases, there is a 50-50 chance always. So in some cases, here at least you are getting some advantage. In some cases, of course, you have to flush it. But it is always better than adding some NOP or adding some bubble or stall. That means you are at least getting, in some cases, maybe 50% cases, you are expected to get some advantage. So this way, in generally, data hazard we handle in that forwarding and stalling. And this is the example of control hazard where we do this type of we allow some predictive operations, and then if not equal, based on that way we take the decision. Okay.
Ma'am,
Yes.
can you once repeat how this is functioning?
This part. Okay. See, this part is clear, right? Why this hazard is happening? First thing you have to understand this branch is equal. Okay. If this is both are equal, then you will be taking the branch. Otherwise, your program counter, like this is a simple scenario when you write in your soft code, if A greater than B, like if gray greater than B, do this, or else do that. Okay. So what happens? PC is having some instructions for this A greater than B, and PC is having some instruction if this condition is not satisfied. Okay. Now you have written this program, you have generated it's a machine code, you have fed that to your hardware. Okay. Up to this part is clear what we are doing?
Yes, ma'am.
So after that, now you have to take a decision. Before instruction execution, you do not know whether based on which value, whether this will get satisfied or not. You do not know what are the values you are having in this register 1 or register 3. Okay. So in that case, if you blindly follow the pipeline execution, what will happen? You will do this instruction, after that and, after that or, after that add, and so on. Now once we are doing, your branching is getting satisfied. Maybe when this condition is false, that means you have to jump to this instruction. Okay. Or whatever condition you have mentioned. That knowledge that whether you have to take the branching or not, that you are not having before this cycle 3, because see, this is your branch if equal condition. This equality check module is a part of your ALU module or associated with your ALU module. So up to there, you will go, you will check the equality and you will get the result. Once you are getting that result, at that time you have the knowledge, okay, now I will take the branch or not. Okay. So in that case, let's say your this condition branch if equal is getting satisfied. That means there is no need of these executions, these instructions. From here you have to just, this is your jumping target, branch target, you have to jump here. Okay. So when you are just feeding them to in the pipeline, initially you have not the knowledge that whether the branching will take place or not. But what knowledge you have that if the branching is taking place, you will of course go to this part. But if it is not taking place, these results will be useful for you. Right? So there is always a 50-50 chance. Branching condition may be getting satisfied, may not be getting satisfied. So when there's this type of hazard, what I was telling, that if you don't know the branching decision up to this point, that means you have to stall the next operations. Ideally, what you can do, you can say, wait, I will execute the branching instruction, I will see what is the result. Based on that, I will tell you, okay, which one to execute, this one or this one. But here we are taking a predictive strategy where we are telling that if branching is there, then of course we will go to this direction, okay, this load word direction. But if that is not not there, the branching condition is not getting satisfied, then this add or add, whatever I have executed, just immediately in the pipeline sequence, that results will be useful. So in that way, I am actually improving my performance with this predictive strategy. Okay. Other than that, what was the solution? You could have added some stalls, and that is actually adding some extra delay to your performance. Okay.
Yeah. Ma'am, can you go to the diagram part? Can you go to the diagram part?
This one. Yes.
So ma'am, the blue line connection is connected to the IR.
Oh, this blue line connection. See, it is telling that if this branch if equal is getting satisfied, then you have to jump to this part. Okay.
Yes, ma'am. But like when we are situation is getting satisfied and then we are jumping to the last part. But
Hmm.
in the meantime, in the clock cycle, the decision is taking place in the clock cycle third. But in
Hmm.
clock cycle two, the
Hmm.
second line has started performing. So the values will get stored, or like it will stop the function as soon as like the program has jumped in clock cycle fifth.
Can you come again?
Ma'am, like ma'am, we are doing the comparison in clock cycle third. Then we are getting a
Third second,
decision
yes.
whether to
Hmm.
jump or not.
Exactly.
So, but ma'am, like in the clock cycle two, the second line has
Hmm.
already started. Like, so will
Yes.
that program get stopped as soon as we are getting jump, or like
No,
will
no,
it
no. It will not get stopped. You have already executed. You're right. You have already executed this and this maybe. But what will happen? That memory, that whatever values you have stored, that part you will flush, and you will immediately start execution from this part. Yes, yes, you can tell it. It will be stopped. I mean, from wherever position a cycle it has executed, from there it will be removed and it will load this part.
okay? So
Okay,
the
maybe if you have.
values will not get changed of the like address 12 and address 2. The values will be removed as soon as we jump to the last part, right?
Yes, yes, yes. Whatever addressing, I mean, the next address at that time, whenever you are getting the decision, you remember this is the basic idea, whatever you have discussed in the previous day. See, here, you are here. You have branch if equal means you have taken the decision. Okay. Now, in this stage, actually, you are getting, that's why 3 stalls we are considering. 1, 2, 3. Here you are getting what will be the next PC. So here this branch taken in information you are giving to this marks, and from there this is the, this maybe 0 or equality check, whatever it is coming. Other than that, this is your instruction of your next PC. So ideally you have already loaded your next PC address, but due to this branching, this is your branching address. And when this decision coming from your this is 0 or is equal, whatever module may be, from this execution stage, that is the selection of this marks. Now these marks is sending the information that what will be your next PC address. That PC address, it's getting loaded to this PC. PC basically what you can think, this is the information program counter is having, from where it will fetch its next instruction. Okay, so this is the idea in this also. This is a branching instruction. Only thing is that when you are doing all these parts, when you are actually doing for your branching instruction, you are doing this part, you are doing this part, and you are doing this part. These are the 3 important clock cycles. What will you do in your pipelining sequence? Because you don't know where you will go next. You don't know whether, according to whatever you written in your instruction set, like all this one, this and this, whether you will go there or you will go to your jumping, sorry, this is not this, yeah, whether you need this or you need this, which path you will go. So that's why this is the idea. Okay,
Okay, ma'am.
is that clear now?
Yes.
Okay,
Hello, ma'am.
yes, tell me.
Ma'am, I am not getting in registers in this diagram from where
Hmm.
this is jumping to which blocks, from which block to which block or which pipeline.
Okay, in the pipeline, which this diagram
Yes, yes, ma'am. This diagram only, ma'am. You
or
have
the
written
previous diagram?
40
Huh?
BEQ. Is, ma'am, here it is written that 40 BEQ $1 comma $328. Ma'am, this instruction, if this condition is false, uh,
Hmm.
it will jump to this 72 LW $4 type command.
What come again?
Ma'am,
This
if
40,
the
44, they are just the instruction number. They are the just locations. This is not. This is your instruction.
ma'am, I am ma'am,
Yeah,
please,
tell me.
ma'am, this instruction line, 40th instruction line, ma'am, where it is inserted or in the block, in the
Okay.
ma'am, in the diagram, and from where, and if it is false, then where it will be jump in the block, ma'am. I am getting in instruction wise, but somewhat confused in blocks.
In this diagram, right?
Yes, ma'am.
This diagram is confusing. Before you were clear. You know how to execute a branching instruction? Okay. Tell me. Is it clear? Is
Yes,
this
ma'am.
diagram? This is clear, right? You know how to execute one branching instruction, right?
Yes, ma'am.
Clear? You know what does it mean? The arrays, RT, all these things. Clear?
Yes, ma'am.
Okay. So now just sorry.
I'm only somewhat confused. So, ma'am, please.
Okay, no problem. I'm repeating. This is a bit confusing actually. See, come again. This is a branch if equal. So branch if equal means you will be checking two values from two registers here, 1
Yes,
and 3. Okay. And
yes,
then
ma'am.
what you will do, if they are equal, you will be jumping to some location.
Yes, ma'am.
Okay. So that is the idea. Here it is early written 28. So some instruction you are telling. Okay. There
Ma'am,
logically.
ma'am, where is 1 and 3 is stored in the blocks? Ma'am, register just above first line register or second line register. Ma'am, where?
Here, okay. This is for these. This is entirely for your first instruction. Just focus on this first line. Forget about the
Yes,
next one. Okay.
yes, ma'am.
Here it is 1 and 3. So
Yes, ma'am.
first, what you have to do, you have to know that what is the value in your register. Fetching the, remember to come back again with this. Always map this memory. So see, in your instruction page, what you are doing, you are fetching data from instruction memory, right?
Yes, ma'am.
So for this is the instruction IM, which is better. After that, next what you are doing, again come back. Here you are having some register. From that register, you are checking from your instruction, whatever. See, you have fetched that register in your instruction register. And now you are checking these bits. RS, okay, your register values. So that registers you will fetch from this register file, right?
Yes, ma'am.
Now you come here. Okay, where is that? There. Okay. Then that means that's why it is written REG. That means this is your register file from where in this instruction decode stage you are basically fetching those values, whatever they are in your 1 and 3. Correct?
Yes, ma'am.
Is it clear? Next, we are going to the third part, third cycle. Here, you can see this is the symbol of ALU. Okay. Now, what you have to do? Your equality check module. We are assuming equality means some mathematical operation. Is maybe equal, maybe addition, subtraction, whatever it may be. We do in this execution phase. Okay. So here you are doing this operation, and that operation is going. Then next, what you have to do? This result, whenever you are getting that result, now come back to this diagram again. Maybe you can see this diagram, the same diagram, just you have to focus on this part. Whenever you are getting from your ALU output, that is whether the equality result is 1 or 0. That means values of these two registers are 1 or 0. So if it is 1, what we have to do? According to our instruction,
Ma'am, which registers, ma'am? Please tick the registers. I am not seeing the dot.
no, tell me, you can see this instruction, right?
Yes, ma'am.
BEQ $1, $3, that you
Ma'am.
can do, right? You can see, right?
Yes, ma'am.
You can see. So if the two values in the registers are equal, what we will do? What is the
Ma'am,
instruction?
condition is will be true.
Condition will
So,
be true, right?
so
So what
ma'am,
will happen?
48 and 52 will be executed.
Which one executed?
Ma'am, these three, 44,
3.
48. Oh, ma'am, this next instruction means and $12, comma 2 will.
Anding will that get executed? Think properly. It is telling that branch if equal, and I am telling you whatever value we have stored in $1, that means register 1 and register 3, those locations, those are
Yes.
equal. Then what will happen?
Oh, ma'am,
According
so
to your instruction, see the instruction, this is branch if equal.
is
Branch
equal.
if equal, see BEQ.
Yes, ma'am.
That means some branching will take place.
Yes, ma'am. Okay, ma'am. So, ma'am, it is LWS for $4.
Exactly. There it will jump. That's why that time these instructions will not be required. Now is
Yes,
it
ma'am.
clear? Yeah. Clear, right?
Yes,
Now,
ma'am.
since in the immediate next pipelining stage, we do not know which one is going on, which one to execute. That's why we are actually taking the help of this predictive analysis, and we are executing these instructions, and we are, once if not required, we will be flushing it. So that is the idea.
Yes, ma'am.
Clear?
And ma'am, one more thing
Yes.
I want to ask that this block diagram which you have made here is the same that you are that the diagram is somewhat colored green or
See, these are just the representations of this. Yes, those are same.
yes,
See,
ma'am.
what are the stages I have shown here? Instruction fetch, instruction decode, and register fetch. You can see. Then
Yes, ma'am.
execution, then mem, and then write back. These are the 5 stages of pipeline. Since we are only focusing on MIPS, we are just considering these 5 stages. Okay,
Yes,
there may
ma'am.
be some differences in this. You can, write this, right? Now you go here. Here also these 5 stages. Instruction memory means it is denoting that instruction fetch part, that is you are fetching from memory. So the same thing, only the symbols they are changed. Register, you are fetching from the register, basically decoding part. This is the decoding part. This is the ALU part. Next is the data memory. This is the memory write back part. And this is the register write back part. Or memory access part, this is the register write back part. So these are same as whatever diagram is there. Not this one. I mean this one. Everything is the same diagram. Clear?
Yes, ma'am. Yes, ma'am. Clear.
Okay.
Thank you, ma'am.
Any other question?
Ma'am, just one. Like
Yes.
you said like as soon as the branching takes place, the other values get flushed, right? The three values. But then, like, do we is there a need to add something, or like it will get automatically flushed? Like, how is the program?
No. The next slides will give you the answer. I'm not going because this pipeline itself is a huge subject. So if I go detail, I am just giving here the idea because I have to go to the embedded software. Just give you that idea. Yes, that is nothing is automatic. For everything, for every modification, this is the hazard detection unit. That whenever you are doing this type of predictive study, predictive decision making, for that also you are trying to you are adding some detection units here. See, this is a forwarding unit, the forwarding unit that I have told. So these separate discipline units, and there are some added controls also. Okay, you can see here some added controls. So these separate modules, this is not your exam purpose, don't worry, because no need to think and remember all such huge circuits. Just to give you huge diagrams, just understand what is the purpose of these different modules. So there that we are as and when we are adding these type of implementations or the hazard handling strategies, basically we are adding some added modules to that hardware, and those components are actually taking place for this forwarding, for this stalling, or for this added control, that when to flush, what to discard, what to keep, everything. Okay, so these are the added hardwares, just to give you some idea. Okay. Okay, so this was I mean, about pipeline. Just go through it. If you have any question again, just come back and ask so that we can again discuss. Okay. So this is what we have talked about, everything about hardware level parallelism. In our backend hardware, we have added some extra registers. We are with some extra controls. We are storing data, extra some units. We are handling hazards. Whatever doing at the backend, we are analyzing our instructions, whatever requirements, and then we are modifying this our pipeline hardware. So whatever parallelism we are providing, that's from our hardware support. So next, another level of parallelism, when we actually do the write the instructions or handle the instructions, that comes from instruction level parallelism. But always, I think at this stage, you can understand these type of parallelisms also is never possible if you do not give any support from the backend hardware. Because ultimately, whatever, it is like front end and back end kind of thing. Whatever you are writing, whatever modifications you are thinking in your front end, maybe when instruction level or your compiler level, of course that must have some support from your back end. And that, I mean, or you are somehow manipulating. We will see in our support parallelism, we are manipulating whatever hardware you have, whatever components you have. So that way, instruction level parallelism we apply in different types of instruction sets. One is CISC, CISC, where the instruction itself is very complex. That means nothing but we are adding huge, smaller operations in one cycle instruction. Okay, sometimes that to do that, whatever ALU support you have, in that ALU, you are basically at a time simultaneously maybe using multiple components, or sometimes you are considering the presence of multiple ALUs. So other than whenever you have some smaller operations, you are clubbing them and you are mapping them to some complex instruction. So at the back end, again, you have to think about how these complex instructions will give that operational support. Okay, so that support should come from maybe if it is a single ALU, so your instructions should be like when you are forming that instruction, like how you are basically efficiently use all the components at the module, because whenever your adder is busy, may not be the case that your multiplication module is also busy. So is it possible that one instruction we can parallelly do some addition and multiplication, and then we combine some result and we develop some complex instructions? Or we have some multiple ALUs, that two ALUs may be supporting two different multiplications, and together you are combining them and you are telling them, okay, see, this is my complex instruction. So this is the basic idea, that whatever instruction level parallelism you are doing at the back end, you have to keep in mind that is my processor, is my actual hardware giving that support for that. So another one is, this is a subword parallelism. I can tell that this is how you're manipulating your existing hardware, what you have. In case of 64-bit ALU, if we can take this simple example, we can understand. If we think about this type of image processing or this type of examples, where we have to deal with this RGB format, where each of the bytes, it can be represented only with 8-bit numbers. So when you are just processing on one of them, you are just processing on some 8-bit value, but this processor actually you are using 64-bit. That means there's a clear wastage of your whole 64-bit data path, or say 64-bit supporting ALU, everything. 64-bit supporting memory. Maybe memory you can efficiently store, make some storage, some storage strategy you can design and you can store. But for your data path, which can support some 64-bit together, that is just passing effective 8-bit values at a time. So there's a clear wastage of your whatever resources you have. So in that case, what we do, this is the subword parallelism. Okay, what we are doing, if I have 64, we are just dividing into subwords, and we are performing some operations on the subwords, not the whole part. So that this is called the subword parallelism, where instead of changing much, whatever whole resource I have, we are dividing those in smaller subword slices and performing operations. Okay. So in case of vector processors, or in there are some Intel processors also nowadays, they support subword parallelism. Okay. Another concept is superscalar or very large instruction word. So in both of the cases, what we do, again the same thing. We are basically combining multiple independent operations into single instruction. Okay. So multiple smaller operations you had. So initially you were telling them, okay, see, these are my instructions. Maybe addition is one of my instruction. Now you are telling, no, I have I'm combined one addition and some few multiplications together, and this is my single set of instructions. But in whatever be the case, again you are modifying your ALU also accordingly. Or another important support, this type of superscalar execution type of processor they follow, that is called out of order execution. That is mainly dynamic. When you are you are combining these multiple independent operations, but those in the dynamically, the runtime. When you see that, okay, some later future instructions, that is not, there is no dependency, and I can take it forward and I can club with my present instructions, and I can send them to my ALU to get executed simultaneously. Okay, so these are out of order executions. Of course, that is only possible if there is no dependency. So these are few techniques we take from the instruction level, combining smaller operations to single instructions, or applying subword parallelism, performing out of order execution. So these are few typical strategies we take when we consider our when we are actually providing parallelism from instruction level. That's why this is called ILP, or instruction level parallelism. Now, finally, the final type of, mostly in the embedded scenario, you have seen chip, you have some FPGA code, you have some software code. So there are different multiple cores, and we are taking, since this IC development is improving day by day, so we are taking the advantage of that, and we are considering multiple cores. We are trying to make our design in such a way that maybe we can offload some part of our design to our soft code. We can offload some part of our design to our FPGA code. That is field programmable get array. There we can take the support of huge amount of parallelization. We will discuss this in our lab also, that what type of parallelization we can actually apply in case of FPGA design, and that will also improve our overall performance. So these are the few typical aspects, typical possibilities we can explore when we are trying to choose our development, when we are trying to choose our implementation of our software. That when first we have to check that whenever I am designing from your specification, maybe you are designing one software. Okay, you have some specification, you know what is your performance requirement, what is your real-time performance criteria. And you can see, if I directly implement that in my soft code, it may happen you can never meet your deadline requirement. At that stage, what we do, maybe some complex or some those are parallelizable, that we can actually parallelize those parts that we can actually offload. So this kind of FPGA platforms, and we try to do hardware software co-design. Maybe in the latter part of this course, Professor Sharkar will be discussing this. But the main idea is this: you have multiple cores, divide your specification, offload in different parts, and then combine the result, so that obviously you can expect to get some better performance. Okay, so this way, whenever we are writing any embedded software, the first thing, which processor we will choose or which combination of the processors we will choose comes from basically analyzing these type of decisions, these type of architectures, or these type of solutions what we have. Okay, so that ends the discussion about our embedded processor. You can check with these references. Any questions from this part?
Ma'am, last point. What is the meaning of off-the-shelf processors?
Okay, off the shelf means here, see, you have one IC, maybe connected ICs. There you
Yes.
have two cores, FPGA and one soft core. So
Mhm.
when we are actually considering some operation, your design to be divided, if you divide that in this soft core and your FPGA core of that same IC, then
Yes.
their interfacing, their communication, everything is, optimized already from your manufacturer. Okay, but
Yes, ma'am.
here, otherwise, what you can do, you are typically doing some software development and separately doing some FPGA development, and then you are combining them. That is the off the shelf, your other core you are using. In that case, there may be some interfacing issue, or this communication may not be optimized in that way. Okay, we
Yes, ma'am.
will discuss about embedded communication maybe that time. So at that, so of course you can expect that time, you can expect when you are going for this off the shelf course. Of course, sometimes we have to do it. We do not, if we do not have option or whatever multi-core options we have at hand, if it is not, I mean, what to say, if it is not enough for our requirement, then we have to go for the off the shelf FPGAs or some other cores coming off the shelf. But otherwise, we will be in IC. We will be focusing on in IC, our own IC codes, if we can manipulate them properly and we can come with our development. Okay.
Yes, ma'am. Ma'am, what is core, ma'am, physical meaning?
Core means you can think that there's some processing unit where you are actually doing the processing component. Okay, multi-core machine. Okay,
Ma'am,
different process.
not
Yeah.
visualizing anything.
Hmm? You are?
Uh, Ma'am, not getting the physical dimensions or
See, multi-core architecture means, see, either maybe you are, let me see. You have see, maybe in your IC you have some part where you can execute your embedded software directly, implement
yes,
your embedded software directly, or some part of your code you can execute in your FPGA part. FPGA, no, right?
yes,
Field
ma'am.
programmable gateway. So these are the two different cores where you are actually doing your processing. So these are your you can think about multi-processors. Okay,
Yes,
different
ma'am.
options of your where you can offload your processing. So these are different cores. In your system server also you can have multiple cores. It is not always that you have to cores means something is of related to hardware and something related to software. No, in your software system, software server can have multiple cores where you can divide and offload your processes.
Okay,
Okay,
ma'am. Get it. Thank you, ma'am.
any more question?
Hello, ma'am.
Yes.
Ma'am, as we have discussed in like very large instruction word, we do manipulation of multiple operation in a single instruction, and same
See,
we talk.
I told we can combine multiple
Yes,
smaller operation in, yes.
yes, and same thing, ma'am. We said like same thing we talked in subword parallelism also.
No, not that. In subword parallelism, what we do in we are basically doing the same instruction. Okay, same instructions we are applying. Like you have 64 bits. Okay, in there you are dividing that 8 bit, 8 bit, 8 bit, 8 bit. Now you are processing each these 8 bit sub parts together. That is the concept of subword parallelism. Okay, in case of what to say, multiple instructions, what you are doing, you are combining smaller multiple operations, and you are trying to finish them in same instruction cycle, and that way you are considering that this is a single instruction together, and that is giving you the output. That means when you are writing, you can think in a simpler way. Whenever you are writing a code, you actually use the instruction sets of whatever processor you are using, right?
Yes, ma'am.
So in that way, what you do, you take that particular instruction as a single instruction, right? And here you are actually applying that single instructions on that subwords. Here you are thinking that your ALU is sliced and is capable of actually operating on those subwords. So there's a little bit difference.
Okay, ma'am. Okay, and ma'am, one more doubt I have.
Yes.
Yes, ma'am. Ma'am, and in programming language, like most of the programming languages, instructions are being executed sequentially, right, ma'am?
Yes.
Yes, ma'am. So how could we like achieve parallelism in that case, ma'am? Like if the instructions are being executed sequentially.
So that's what we have discussed. See, you are writing everything sequentially. Okay.
Yes, ma'am.
So here, whenever we have talked your instructions, maybe now you understood, right? When we are transferring those your instructions to the hardware, it is some way in the form 1010. That's some sequence, right? But that also sequentially as in the form you have written your instructions. So directly we cannot do in a software. Software is not for providing parallelism, because if you think about thread libraries, by that way we provide parallelism, right? But that is basically in the underlying architecture, your hardware is taking care of parallelism. So whenever you are thinking of parallelism, basically your compiler or your intermediate processing units, they are mapping them to the hardware. And here we are providing the parallelism with the help of pipelining. That's why this you can think about, you can see this diagram. Oh, wait. Yes. This is, see, these are, yes, you can leave. I mean, we are done. So you can leave. So maybe just Pratiksha is asking this question. So I'm answering. Okay, no problem.
Thank you, madam.
Okay. See, here your instructions are sequential. 1, 2, 3. These are your instructions.
Yes, ma'am. Right.
Okay. But what you are doing, underlying operations, intermediate operations you are breaking, and you are taking again the support of hardware. See, we are adding extra registers. So basically we are taking the support of the hardware. Okay. And we are breaking those instructions in such a way that we can add parallelism to them. But ideally, from the software point of view, whatever you are writing, they are actually executing sequentially. That's why this is hardware parallelism. You are supporting parallelism through your hardware.
Okay.
But
Okay,
whenever
ma'am.
you are
Got it.
writing anything in C or Java, everything is sequential.
Yes, yes, ma'am. Got it.
Yes, yes. Okay. So that's all for today. The next day we will start with the memory discussion, and then I will answer the Pete Weber's addressing and all. Okay. Thank you.
Thank you, ma'am.
Thank you, ma'am.